You said that now the crystal, I want to show you something. Here is what happens. Here is the electron. Here is the electron, and here is the electron, and so on. The electrons generate the ultrasound that you will then use in the process. This depends on the change in the orientation present in the crystal. This change in orientation compresses the surface of the crystal relative to the surface of the probe or the surface of the transducer. This pressure generates ultrasound balls that come out of the transducer, and then imaging is performed for you. So this is the production of the ultrasound pulse. The pulses that come out of the ultrasound have a specific frequency, a certain frequency, and a specific wavelength. We said that any pulse is a sine wave, and the distance between two peaks, the peak-to-peak distance, is called the wavelength. So, how many cycles per second is this frequency? How many cycles will pass? This is the frequency. Now, if you want to generate an ultrasound pulse, for example, with a certain wavelength or high frequency or low frequency, then you should choose the thickness of your crystal. A heavy crystal should equal half the wavelength of the ultrasound. Do you understand this information? Half the wavelength of ultrasound means what? This is half the wavelength. What does this mean? The crystal that you have is sufficient. If you want to produce a high-frequency pulse today, you simply need to use a thin transducer or thin crystal. Why? Because, as I mentioned, when my crystal is small, I said the thickness of the crystal is small, which equals half the wavelength. This means that my wavelength will be small, which means my frequency will be high. My frequency will be high because there is a relationship between frequency and wavelength. If your thickness is small, the wavelength will be small, so the frequency will be high. Frequency is the number of cycles per second that will appear for the pulse. If you choose a thick transducer or thick crystal, the wavelength will be large, so the external frequency will be low. Why is the idea that you must choose a crystal with a thickness equal to half of your wavelength important or not? You all need to understand this. Let me tell you the solution. Here is the thickness of the crystal, and here is the frequency. Notice here that when the thickness was 1 millimeter, the frequency produced was 2 megahertz. Now, as we decrease the thickness, the frequency keeps increasing. Therefore, the wavelength keeps decreasing. So, there is a direct proportionality between thickness and wavelength, and there is an inverse proportionality between frequency and thickness. Why do I say that again? This is the shape of the crystal from the inside, and these are the crystals present, 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 and this is the process of applying the electric field and our on and off, which is controlled by the thickness of the crystal present. Now let's go back to that part. I am, as you know, a doctor. No problem. Of course, inside the probe itself, when you open the probe, you will find that there is not just one crystal. The one I have contains over 500 crystals. The specification, for example, I will show you that you have a probe that you use for Doppler and a probe that you use for the abdomen. There are also probes used for shallower imaging or for surface imaging, and others that you use for deep imaging, right? The entire team is challenging this frequency, meaning when I came in, I wanted a high frequency. We always use high frequency for shallower things or for surface imaging that requires high resolution, for example. So I use the probe, and the probe itself has crystals. The thickness of these crystals is what gives me the high frequency that I want to work with. Is that clear, doctor? Or should I explain more? The probe? Okay. But the probe itself is not just one crystal inside. I want to show you an image. For example, here is the shape of the probe. I have it here. Here is a crystal, and here is another crystal, and here is another one, and here is another one. All these are crystals, but they all have the same dimension or diameter. So I determine according to my size, because of course each probe has its own crystal diameter that is related to it. So when I speak as if I am talking about the probe itself, right, doctor? Okay, fine. Now, the ultrasound pulses emitted from the crystal do not appear in one direction. They are emitted in all directions. For example, when you look at the probe, you see that there are pulses appearing in various directions, and there are pulses that return. You find that there are pulses that penetrate and continue to penetrate repeatedly. This is why there is something called backing material or backing block, which has a property known as acoustic impedance. We will talk about it shortly as it expresses the ease or resistance of the pulse's movement within it. This means that the returning pulse to the probe itself, or the one returning within the backing block, if this pulse encounters a difference in acoustic impedance when moving from one medium to another, reflection begins to occur. Therefore, to prevent the returning pulse from reflecting or bouncing back. In summary, it moves and shifts inside the probe. I want it to be done so that it doesn't return to do it again here. They make it from the same material to prevent it from happening again and to avoid going back in that direction for me. Now, the part I want to talk about is something we discussed a little while ago. The crystal, for me, works like this. All right? I say that the thickness of the crystal should essentially equal half of the wavelength. So if I increase my crystal a bit, what will happen? Simply put, if I say half, I mean half of the wavelength. Now, in essence, I have this cycle, right? The wavelength is the distance of one cycle, or the distance between two peaks. It is the same distance between two peaks or two bottoms present in the wave. This distance is considered the wavelength for me, or the two bottoms are the wavelength for me, or the distance of one cycle is the wavelength for me. All of this is the same. So, if I want the crystal to have a thickness of half the wavelength, what does half the wavelength mean? It means just one peak moving through it. So, come here. As I mentioned, I have a projection in all directions. So it can come out like this. At the same time, it can come out from this surface like this. Now, if I have the crystal, for me, the thickness of the crystal is equivalent to the wavelength, meaning it equals the wavelength for me. They said something called distractive interference will occur. Distractive interference between the waves or between the ultrasound pulses that are present. What does distractive interference mean right now? If I have an ultrasound pulse like this, and there is another ultrasound pulse like this, what will happen to pulse A and pulse B is that they will cancel each other out. I call this distractive interference, and I refer to these two as autophase, slightly. This means that every pulse you refer to from the second pulse, in this case, both cancel each other out. In this situation, I have eliminated my pulse, and I won't be able to create my pulse, so I call it that. Now, if you choose from the larger one, this means you have made the phase in which it will move complete from the pulse that will start the cycle when it approaches. Because it has production at a certain surface of the crystal to the other surface, it starts to become out of phase with respect to the pulses that originally exited at the other surface. How does this happen? The whole idea is that I want to make the thickness of the crystal accommodate only half a cycle, not a full cycle, just one peak. So when my wave exits, it should be in phase with the cycle that is already being produced on that surface, thus avoiding any distractive interference. However, if it is too large for me, then I have something present inside. The complete cycle means your crystal has become large enough, so what will happen is that the wave will start to emerge, or the cycle will become in phase with the main cycle on the surface of the crystal for you. Match half of the cycle. You want to avoid pulse interference. In this case, you will generate two pulses in phase. If there is a difference, constructive interference will occur between the waves and the pulses, resulting in an increase in the strength of the waves without any fading or loss. Does it fade from the crystal? It doesn't happen, or it doesn't happen, right? There are two types of motion that can occur in a crystal, one called thickness mode and the other called radial mode. This motion can be like what you see here, which is from top to bottom, or the radial mode, which is like motion in all directions or in every direction concerning the crystal in this way. This is called radial mode. It means that the motion occurs in all directions. The crystal behaves in a thickness mode, which is from up to down, And this can be the compression or motion that occurs. Now, let's talk about the sound pulse, or the ultrasound beam that has specific properties, a certain speed, and this speed is determined based on the media it travels through. It has a frequency, which is the number of cycles per second, and a wavelength, which is the distance between two crystals or two bottoms, and it has a certain amplitude. The amplitude represents the highest energy or the highest pressure present. You see the area that is considered the region that expresses this. All right, let's move on to a specific sound. For me, okay, oh yeah, that's it, okay. In the context of the number of cycles, it is a product of frequency and wavelength. Frequency multiplied by wavelength. Now, I say that the frequency from 2 to 18 megahertz is what I consider using in medical ultrasound. So I say the frequency number of cycles from 2 to 12 megahertz is what I consider using. Hertz means the number of cycles per second. If I have 1 cycle per second, it means 1 over t. So in this case, frequency equals 1 over t, where t is the period of the cycle. If you have the frequency, you can find the time, which is the period of the cycles you have. If you have a number of cycles, if it's 1, then it's 1 over t, which gives you the time for 1 cycle. This is the relationship between frequency and the time of 1 cycle. If I call it periodic time, the ultrasound pulse takes this shape. This is the pulse that comes out, and you will find that there are 2 things. One is called center frequency, and the other is called bandwidth. What is the center frequency and what is the bandwidth? For example, in the probe, if you open the specifications of the probe, you will find that this probe has a specific center frequency, which I call F0, which is this value. And it has something called... The bandwidth is the range of frequencies that come out with the pulse, meaning the pulse itself has a frequency, but you can select the preferable frequency for you, which is the central frequency, F node, at the maximum. So, can you choose any value from the frequencies within the bandwidth? Yes, you can, but this varies from one probe to another. The Q factor is present according to a need, and we will talk about it shortly. It determines the bandwidth of the frequencies present, specifying whether the bandwidth range of frequencies is large or small based on this Q value, or Q factor. When we talk about the speed of sound waves, what is it essentially determined based on? The medium in particular. The medium can be, what is this medium? It consists of bonds that exist between these atoms. Now, let's say I have, for instance, for example, this red circle which represents my atoms within a certain medium, and I have a bond that connects my molecules. Now, if I introduce a sound wave, it will travel from molecule M to the next molecule, and to the next, and to the next, and so on. In this case, there are very strong bonds that exist between them in this specific context. When I provide energy or a sound wave to the first particle, it is in fact very easy for this sound wave or energy to transfer to the next molecule because there are strong bonds between them. All right, so let's take a moment to consider what we're dealing with here. We have a situation that requires our attention and understanding. It's important to acknowledge the circumstances and approach them with a clear and open mind. By doing so, we can ensure that we are fully prepared to address any challenges that may arise. Let's proceed with a thoughtful and deliberate approach, keeping in mind the significance of our actions and the potential outcomes they may bring. To create a small red circle, here in terms of mass, while the stiffness is high, meaning there is a strong bond between the molecules. It's like when you have one person holding the hand of another. If you push the first person, everyone holding hands will move together. But if there are people not holding hands well, and you push the first one, the energy won't transfer. This is the same idea that happens with the bonding between molecules, which I refer to as stiffness. Its effect is very high on the speed of sound waves or ultrasound waves within the medium. Its impact is very significant and greater than the density of the medium. For example, you might hear someone say, the speed of sound is equal to the density of K divided by ρ, where ρ is the density of median and K is the stiffness. This means that there is a relationship between stiffness and the speed of ultrasound. If stiffness increases, then the ultrasound speed will also increase. What happens to the ultrasound speed? Well, there is also an inverse proportionality between the ρ, which is the density, and the speed of ultrasound. This means that if the density increases, the speed will also decrease. There is an inverse proportionality between C and ρ, or the square root of ρ. You said yes, your statement is correct, but the effect of stiffness is greater than the effect of density. It means that the amount of increase in the speed of sound due to an increase in stiffness is greater than the amount of reduction in the speed of sound due to an increase in density. For example, take bone. It has high density and high stiffness, but at the same time, its stiffness is high, so according to this equation, with high stiffness, the speed of sound should decrease. However, because the stiffness is high, the speed of sound increases in bone. So, what's the issue? It turns out that stiffness has a greater impact, which is why you will find the speed of ultrasound in bone is higher than in other tissues. Another example, if you increase the mass, meaning you increase the ρ, but your K is weak, you will find that the speed of ultrasound decreases because the particles are not tightly held together, even though the density is high. The particles are just not holding onto each other tightly. The bond is very weak here because the stiffness is relatively low, so consequently, the speed of sound will be quite low as well. What we understand from this observation is that wherever and whenever a medium happens to be compressible like air, then naturally speaking, with lower stiffness comes a correspondingly lower speed of sound propagation through it. That's precisely why air has large spaces between its atoms, which leads directly to weaker bonds existing between them in such cases. In this particular case scenario, the transfer of energy or ultrasound pulse, or even ultrasound energy, in an airy medium will indeed be notably weak compared to something denser like bone, which, despite being high density, possesses strong molecular bonds within itself. This results ultimately in faster transfers occurring for both sound waves and also ultrasound waves. So, a box is necessary for me. That's why you'll find a lower value of 1,578 meters per second for the stiffness of 1,560, the previous value of 1,430, the average between the tissues I use, and this value is very important, which is 1,540. This is the average for the tissues for me. The water is 1,480, the bone is 3,000, 480 for the bone, 3,190 for the air, and 330 micrometers per second is the lowest because it is the most compressible material, or the one that can have a weak result. Thus, the energy transfer will be weak, and consequently, the speed will be as low as possible. Is this clear, doctors? So, the velocity of the sound wave is dependent on the material itself, on the stiffness, and on the density. As we said, this is the average value I use in the calculations, which is soft tissue. So, Why do you use this velocity? Simply put, in a straightforward manner, I want to begin by thoroughly explaining the various initial uses of ultrasound during World War II. They used ultrasound to ascertain the precise locations of their targets in the vast and unpredictable seas. For instance, a particular type of submarine would send out ultrasound waves. Let's say, hypothetically speaking, I have a ship. This ship would navigate through the water to accurately identify a specific target. Upon successful identification of the target, it reflects the waves back to the source. It starts receiving the signals and provides information on the duration it took for the waves to travel to the target and back. For instance, it took a certain amount of time